dear colleagues, traditionally in Bulgaria and probably in the other countries, if somebody is elected for a full professor or associate professor, the person should give a talk about his or her research, his or her once Jörg Koppitz was elected a week ago for a professor, and now he has the word for this talk, which is on algebraic properties of transformation semigroup.
Thank you very much. At first, I want to thank all people which have supported me in this time to prepare the documents and to bring me to the way that I apply for this position and help me in all this time. And I'm very glad that I could get this position now. And I'm very thankful all people which have supported me. So, okay, and now I want to start with my presentation for this lecture, which is related to this position that I got it. I want to speak about algebraic properties of transformation semigroups. I want to tell you what I'm doing and in my research, and give you some recent results and some overview what is the subject. So okay, and okay, so okay, I want to start with the following things, namely we know in linear algebra, we are very interested for a vector space for the basis and dimension. So, and the similar things or dual things gives for the semigroups, namely the basis is like a generating set of minimal size, and the rank is like the dimension, namely the number of elements of the sign, the number of the elements in such a minimal generating set of signs. That means the rank and dimension and basis and generating sets are corresponds if you speak about vector space and semigroups. So let S be a semigroup. Then we denote by this G generating set. And what is the rank? The rank is, as I told, the minimal size of a generating set. So, and now the question is, it can happen that we cannot find a finite generating set. It means the rank of the semigroups is not finite. In this case, the rank gives us not enough information or not useful information about the semigroup from the point of algebra. That's why there was the idea of Koppitz in his thesis to do the following, to take a relative generating set. What this means, we look for a subset of the semigroup and ask for a set which we have to add to the set A in order to generate the semigroup. So, and this is called the relative rank of the semigroup S modulo the given set A. This was the idea from Koppitz in his thesis, and is now strong and established in the scientific world. This notation, and many people have looked for this for infinite generated, not finitely generated semigroups. So in my title is written transformation semigroups. Why we consider transformation semigroups? The Cayley, we go back to the group sectors. In the group theory, we know the Cayley theory. That means we know each group is isomorphic to the subgroup to a subgroup of the symmetric group for a suitable chosen set X. So, and this Cayley theorem can also be applied for semigroup. What is the similar for the symmetric group? Symmetric groups are the permutations. So in the semigroups are not the permutations, are the transformations. What are the transformation? Means nothing else as a self-mapping from a set X in itself. That is a transformation, and the set of all these transformations forms a semigroup, which we call the symmetric semigroup. And then we know by the Cayley theorem for semigroup that each semigroup is isomorphic to a subsemigroup of the symmetric semigroup for a suitable set X. So that means if we want to, if we know many things about transformation semigroups, then we know also the things about semigroups. That means the study of the transformation semigroups is similar to the study of the symmetric group in group theory. So, as I told already, that means the transformation is a self-mapping from the set X to itself. And this set of all the transformation forms a semigroup. Now we consider a special semigroup, namely, which is near to the group. So that a semigroup is only a set with isomorphic operation, and we have not the inverse. Now we can imitate such one similar for semigroups, namely that's why that we introduced the concept of a inverse. What means an element is a semigroup is inverse semigroup. That means if I can find for all elements of the semigroup another element in the semigroup which satisfies this both conditions. So, and then we call this semigroup inverse semigroup, and you see this is like a unit here and here, but it is not really this one what you know from the group theory. But this is quite near to the group, and now we have also like a Cayley theorem for such inverse semigroups, namely the following: that each semigroup is isomorphic to a subsemigroup of the symmetric inverse semigroup. What this means? What is the symmetric inverse semigroup? So for this, we need the concept of the partial transformation. Partial transformation means we have a set X, and we take not as a domain, not the full set X. We take a subset A, and then we consider all mappings from the for any subset A, not fixed subset, for any subset A in the set of in the set of X. So that means each transformation is especially a partial transformation, but we have here more. And the symmetric inverse semigroup means that we consider only injective partial transformations, or only injective transformations. So, and so that we have now correspondence between inverse semigroups and the symmetric inverse semigroups Ix for suitable X. That means each of inverse semigroup can embed it in such a symmetric inverse semigroup. Okay, now we want to say some things, some known results about the rank. I mentioned already the set of all transformations forms a semigroup, and this semigroup can generate it if the set X has n elements, then the semigroup can generate it by a half n times n minus 1 elements. So this is a well-known result, very old already, and for the inverse symmetric inverse semigroup, we know that this can be generated by n plus 1 elements if the set X consists of n elements. It means we need only n plus 1 elements to generate it. For groups, we know it, how many that we know only need only 2 elements to generate all the symmetric group. Okay, now we consider particular transformation semigroups. For this, we consider a totally order on the set X. That means, in other words, a linear order. So, and then the transformation from the on the set X is called order preserving. If element X is smaller than Y, this implies the same holds also for the images, or it can be also equal. This is also possible. So in this way, we call a transformation order preserving. And the set of all order preserving transformations we bring together to the set OX of all order preserving transformations, which forms under the composition of mappings a semigroup. In the special case that X is finite, say have n elements, then we say we use this notation On. So, and another well-known result is that we need exactly n+1 order preserving transformations in order to generate all order preserving transformations on an n element set. Okay, this and if we cancel the identity mapping, which is of course an order preserving, then we need only an element. This is the thing which we say this one is the second one is the monoid rank, and the first one is with n+1 here. This is the semigroup rank of the semigroup, and this is the monoid rank, because in this case we every time we have an algebra from type 2-1. That means one element. It means the identity is every time in the structure already, and will not be mentioned as a generator. So okay, let's us consider other interesting transformation semigroup. For this, we use the concept of a fixed point, which play an important role not only in algebra, also in analysis and other mathematical theories. Fixed points means that the image is equal to the input element. So, and then we can bring, if we have a mapping, speak a transformation alpha, then we denote a set of all fixed points by fixed alpha. So this is the set. And now we can look the following. We take a subset Y of our given set X, and we ask for all transformation, which is Y exactly the set of all fixed points. Not are fixed points, I mean exactly the set of fixed points. To be included in the set of fixed points, this is also semigroups which are considered. But here I want to mention this semigroups, which was introduced by Ike for 12 years in the mathematical world. So, and in the particular case that Y is one element set, then we write is we can write as in this form, and this means we consider all order preserving transformations such only P is the fixed point, and then this semigroup is a nilpotent semigroup. I want to say what is a nilpotent semigroup. For this, we need a semigroup with 0. 0 means that we multiply any element from the semigroup from the left or from the right side, and we get this 0. So that is that's what we also know from the natural numbers, and that is also the same. So, and what means nilpotent? Nilpotent means that I can, for each element from the semigroups, I can find a power such that gives this 0. So, and this is of course not more the case in the natural numbers using the multiplications. But if a semigroup has this property, then the semigroup is called nilpotent. And this semigroup O and P here have this property. So, and what is the 0? The 0 element is the semigroup which have the property that all elements go to P. You can see very easy that this is a 0 in the set of all order preserving transformations which have the fixed point P. That is the zero element, and then we can show that because of order preserving, this is very important that we have order preserving, that this semigroup have this property of nilpotent. So, and now we want to mention the notation of Catalan number. Why I want to do this? So that I want to say later. So Catalan number is here two formulas possible, and I give you here the first 6 elements starting by in the series of Catalan numbers, and I start by 0 and so on. This you can calculate this in this way, and we find out this is a result from last year together with a scientific from Thailand in a joint project. We found out that this semigroup have the following rank, namely I want to recall what this means. It means all order preserving transformations which have exactly the fixed point P, and that you can calculate by this difference of two products of Catalan numbers. So this, okay. Now we want to consider other transformations semigroup, namely we consider a particular partially order. So okay, and this order is the so-called zigzag order. You can find this in Wikipedia. That is a very known order, which is called closed to the linear order. In fact, you can think you have in graph theory, you can think you have a path, an ordered path, and each second arrow you reverse, and then you get the so-called zigzag order considered as a graph on the set 1 up to n. So, and I then have this one. You see, if you take the picture, if you have this as a graph, then in each second arrow you reverse. So, okay, and this partial order with this particular partial order we call fence. That means a fence is a set together with a zigzag order. So, and in the last century, some mathematicians considered this transformations. Namely, they studied the endomorphisms. That means fence preserving. And calculate the numbers, how many such transformations which are fence preserving. What means fence preserving? I do it here for the symmetric inverse semigroup, because our research was about this symmetric inverse semigroup. You can do that also for any semigroup. Then the only difference is it is order preserving for this partial order, and if you have not more not more injective, then you have here also the possibility this is equal. So then instead of I, you can write here any transformation is fence preserving if this imply this one. But in our special case, we consider this implied this one, and conversely. So this is like endomorph. We call this an endomorphism as in graph theory. The other one, if you have only one direction, then this is called weak endomorphisms. So this is this definition of endomorphism comes from algebraic graph theory, that we have this if and only if. So okay. So now we consider all transformations in the symmetric inverse semigroup IN, which are fence preserving. So, okay. And we could calculate the rank of the semigroup. This is a project. This one is a project together with people with a scientific from Portugal, and together with some scientific from Thailand. Speak. This was a former PhD student of me, and this for the case odd and even, you see, is quite different. So for even is easy, it looks like easier. And here, this is a project together with Ilinka Dimitrova from Blagoevgrad. So, okay. And this is for the case n is greater than 5. And the question is, what happens if n is 3? Then we have this particular generating set 5. That means we need 5 transformations in order to generate all partial injections on which are fence preserving on a 3-element set. So in each case, if I calculate here the rank, we have also given an explicit generating set of minimal size, means of this size. So this is every time given in our considerations. So okay, now we reduce this the elements in the semigroup IFN. In this, we add the condition we have to be order preserving. So, and if we add also a further condition, namely this image and pre-image have the domain and image have the same parity, then we come to this particular semigroup. So it looks at first a little bit strong what we are doing because it's the intersection of 3 semigroups. But if you see what this means, that in fact that the image are changed, then you want to see this semigroup is quite interesting. And for this semigroup, we have a characterization. In other way, then that means what this means. So we write transformation in this form. In the domain, we have the elements ordered by the usual order. This is not by the fence order. This is by the usual order of natural numbers. And this means D1 maps to M1, D2 to M2, and so on. So, and if you have the situation, then it is in I of n, if and only if the following 3 properties hold. Namely, that the elements in the image are ordered by the same way. So, and then image and domain have the same parity, and moreover, the difference between 2 elements here is exactly 1, if and only if the difference in the image is also 1. So it means this is ordered by usual order, then we make the difference, and this is 1 if and only if this is 1. So this is the other characterization of this firstly looking very strange, strong intersection of 3 semigroups. But if you look here, then you see that is a quite interesting semigroup. And in a PhD project with my PhD student from Thailand, we found last year the following formula for the rank. So, and as I mentioned already, she could also give the exactly, not exactly, she could give n set of n explicit set of generators with this number of elements. It means a generating set of minimal size. Okay. So now we make a jump, namely from finite to infinite. And the fact is that in the case of infinite, the study is not so strong as in the case of finite, because we have totally other methods and totally other results than in the finite case, and not so much results are known about the infinite transformation semigroups. Of course, if you have a finite set, the set of all transformations is finite. If you have an infinite set, all the countable infinite set, you have immediately a non-countable transformation semigroup. So, okay, so we want to consider the concept of orientation preserving in the case of infinite set X. So in the in the case of finite set X, I have to say there is a notation, and the transformation semigroups which are containing entirely orientation preserving transformation semigroups are well studied. But for the orientation preserving case for the infinite semigroup, we found together with a scientific from Portugal and his student a new concept for orientation preserving. So orientation preserving means in the finite case, you can think it is like a circle, the image gives like a circle. What this means for the infinite case. So that means we can distribute the image, the domain in two sets, in the set X1 and in the rest. So that means you make it first, the first part in your total linear ordered set, total ordered set, it means linear ordered set. Then the first part you denote by xn, and this is the rest. So, and then you take the order, the elements in the image have the following property. If x is smaller than y, then you have three cases. X and y both in x1, xy both in not in x1. So then these elements are ordered in the usual order. That means the image of x and y have the same order as the image x and y itself. So, and then you can have the case x is in x1 and y is not in x1. The case y is not in x1 and x is in x1 is not possible because of this order, and we say x is smaller than x. In this case, the order is inverse. In the case x is in the first part and y is in the second part here, then the order will be inverse. So that means you have a point in which you have a jump where is the elements are decreased, and then you have again the order. You have such a jump. So that I want to illustrate in the following example. We take the real numbers. So we want to construct such a semigroup of order preserving transformations. So then we consider, we want to consider an order orientation preserving transformation. So we consider the following case. We have real numbers, and we consider the following rule. So that means we have from minus from the left side until 3, but not included 3. We have this formula. So what happens? That means if you this one nears to 2, and on the other side you have here go to 3. The limit is almost 5. So that means this goes from 1 from 2 to from 0, not from 1, of course, because this becomes becomes 0, becomes 0 here, and then this is so then you have 1 is not in the image. So, and here from the other side, you must look what happens here. 3, you replace here 3, then you come by -5. You start by -5 and goes to -5 until go to infinite. This goes to 1. That means this here runs to 1, and then you have here the image is this open right open interval -5, 5, and 1 is this jumping point. That means here the from 1 until 5 the elements are greater or have this order. The elements from -5 to 1 have also this order, but the elements from -5 to 1 are greater than the elements from 1 to 5. So this is the meaning of such a orientation preserving transformations in the infinite case. So okay, so then we consider the set of all orientation preserving transformations. This is OPX, and all order preserving transformations. It is well known that both have infinite length. That means we need infinite many transformations to generate OPX and OX. So as I mentioned in the beginning, this gives us not so much information. For this one, we are interested for relative generating sets modulo given set. The idea is we want to this subset OX is a subset. Each order preserving transformations is an orientation preserving, namely if A1, if the say A1 from the last one is the complete set X. So then you have order preserving. So that means each order preserving transformations is included here. So that means the idea is we take OX as a subset from the orientation preserving transformations and calculate how many elements we have to add to the order preserving transformations to get the orientation preserving transformation. So this is different from this depends from the kind of order. So we want to have at first a densely totally ordered set. Densely means that I have if I have 2 elements, then I can find every time an element between them. So that means dense order. So and then we have to distinguish that the set X has a maximum element or a minimum element. So if it has a minimum element or a maximum element, the set X is totally ordered, then we have rank 1. That means we have only one transformation to add to the order preserving transformation to obtain all orientation preserving transformations. In the other case, that means I have baser, minimal, nor maximal element, then we need 2 elements to get all orientation preserving transformations from the order preserving transformations. The first one, this was a project together with my former PhD student. He found this result, and this is the second one, and the first one, this one, and this one is a project together with Ilinka Dimitrova from the Wolfgang, as I already mentioned. So, okay, now we want to consider another transformation semigroup which introduced in the 17th by an Australian mathematician, namely Simons, and his name is Simons, and he introduced the concept of transformation semigroups with restricted range. What this means, we consider all transformations with the restriction that the image is in a fixed set Y. So this is the meaning. So, and now we can consider our transformation order preserving and orientation preserving under this condition. That means we say we fix the set Y and we consider all order preserving transformations which have the image Y, have an image in Y, but not in Y, have an image in Y. That means all order preserving transformations with an image in Y. And this means all orientation preserving transformations on the set X with image in the set Y. So, okay. So let now X again infinite chain or infinite partially ordered set. And now we have to consider again the two cases for the subset Y. So in the subset Y, we say at first Y have neither minimum nor maximum. And then we know that the relative rank of this semigroup is modulo. That means the relative rank of the semigroup of all orientation preserving transformations on X with image Y, modulo the semigroup of all order preserving transformations X with image Y is infinite. This is a result by Kitisak in his thesis. So, and now this we know that is not useful to notice. So now we consider the case the set Y has maximum or minimum. And in this case, the result is totally different. We need only one element to add to the order preserving transformations with image Y to get all orientation preserving transformations with image in Y. This is a result in a project together with Ilinka Dimitrova from Bulgaria for 2 years. So, okay. Now I have spoke about the rank as algebraic property. I want to speak about a second very important thing, what is studied from the algebraic point of view for semigroups, namely the congruences. The congruences on a semigroup is nothing else than an equivalence relation, which have this additional property that you have if you multiply positions-wise the elements, then you get again the element in the relation. So take two elements. They are also equivalent definition that you multiply each to take only one element from the relation and multiply from the right side with one element, get element in row, and multiply from the left side with the same element and get again element in row. This is the equivalent definition of this one for equivalence. So, okay. So, and the characterization of congruences is related to the ideals of a semigroup and gives us very important information about the structure of the semigroups and so, and that's why this is studied for the very important transformation semigroups like the semigroup of all or order preserving transformations by Vito Fernandez and a group of international scientifics, and from the same authors also, but some years later, also for the orientation preserving transformations. So, okay, we want to do this for tense preserving transformations, but not only for the finite case, we go to countable infinite case. We say we take the natural numbers and we make a zigzag order on the natural numbers in the way that you have an infinite path, and in each position you reverse the arrow. So then you have a zigzag order on the natural numbers. So, and the set of all endomorphisms on this graph, I want to say in this way that we can also speak in such a case for the graph. We have the set. Here, this is nothing else than a graph. We have this is the set of vertices, and these pairs are the set of each linear graph. And then we can ask for the endomorphism on the graphs. And the endomorphisms of the graphs are nothing else than the fence-preserving transformations on the set. So, and by a project with two scientists from Thailand, we found out that we have uncountable many congruences on Fn, and in additional, we could find 7 maximal congruences on F. Unfortunately, we could not prove that is all maximal. We guessed that is all maximal one, but we could not prove it up to now. That is all maximal congruences, the 7th one. So, and considering the congruences, I want to finish my presentation by other semigroup, which I mentioned already in the beginning of my presentation. And for this one, we have found some information about the congruences. So we have again a totally ordered set, and we consider the concept of order decreasing or a transformation. Order decreasing transformation means that the image is every time greater than the input. Such transformations are well studied by several mathematicians, in particular by a student of Howie, namely Umar, and he have very well studied the semigroup of all order decreasing transformations and related transformation semigroups. So what we want to do is the following. We consider from dx is the set of all order decreasing transformation on in the set of all transformations. So this forms under the composition of transformations a subsemigroup. So, and then we can make the intersection of order preserving and order decreasing semigroups. Yes, and this gives us again a semigroup, but this semigroup is called Catalan monoid for the case that X is a finite set with n elements. Why this is called Catalan monoid? The reason is quite easy. The reason is here. The number of elements are exactly the Catalan number. So the number of transformations which order preserving and order decreasing is exactly on an n element set is exactly the nth Catalan number. So, and now we do the following. We take idempotent from the Catalan monoid. So idempotent means the square is the element itself. So, and then we consider the following subsemigroup of the Catalan semigroup, namely that the fixed element, we take all elements from the Catalan monoid which have the same image, the fixed point as the image of this idempotent. It means for each idempotent, we construct a subsemigroup of the Catalan monoid, which have the property that the fixed point exactly the elements in the image of this idempotent transformations. So, and this semigroup is shown not by us, by some other people, mathematicians from Turkey. This is maximal nilpotent subsemigroup of Cn. Cn itself is not a near is a near potent semigroup, and then we look for the maximal nilpotent subsemigroups, and this is given by this construction. That means each idempotent gives a maximal nilpotent subsemigroup. So okay, and what we have done this maximal nilpotent subsemigroups and consider the congruence structure. So the set of congruences forms the lattice under set theoretical point, and then we ask for the minimal and maximal congruences. So, and to find all congruences was unfortunately not really possible. For this is the structure of this semigroup too complicated. But for minimal, maximal, we could found it. Namely, we consider the following transformations. Namely, for all elements which are not a fixed point and which is not the neighbor of a fixed point, the difference between image and a domain is exactly, or not exactly, is greater or equal than 2. So, and this we consider, and then we could find the following characterization of the maximal congruences, namely it's all congruences which contained this set as an equivalence class, and we have, or not as an equivalence class, but there is an equivalence class which contained all these transformations, and we have only 2 equivalence classes. These are the maximal ones. This is a project with scientific from Konkani University in Thailand, and for the minimal one, we could find also characterization for the minimal congruences. So, okay. This is what I want to say today. Thank you very much for your attention. And
thank you very much for your talk. Do you have any questions or comments? I want to make a small remark. I just wrote in the chat that such kind of lectures, inauguration lectures, were introduced in Sofia, at the University in Sofia in 1904. And,
okay.
Yeah.
At the time when I was an undergraduate student, of course, these were very odd years. You know, I don't remember to have seen announcements.
Okay, this is 194, 190 years ago.
Yeah,
Okay.
so it's might be, yeah.
In the journal of the university, there is one volume devoted especially for the first 16 lectures which were published before 1960 or something like this.
Yeah. So it's also possible that the tradition was suppressed or changed, or probably not so visible to students. Yeah, at that time, I don't know. Yeah.
In algebra, we have this, so it's okay. Do you have some other comments? I see that Osman has a comment. That thank you for the good presentation. Some other comments or not?
I have a question.
Yes, sure.
I first would like to thank Jörg for his style of presentation today, which was understandable even to myself. I'm not a combinatorics person, not an algebraic person. I wonder if Jörg, if you have a favorite source of example semigroups, because Of course, to be speaking about algebraic properties, you have to look at axiomatically defined classes. And many theorists look at examples only in order to refute conjectures. But there are also classes of examples which produce applications. So I wonder if you have a favorite source of examples.
What you mean with source of example? I'm not.
For instance, in a very broad sense, computer programs are form semigroups. Yeah.
Yeah.
There are other semigroups which come from other applications. Yeah. So for instance, from I don't know, but I'm focused on computer programs. And typically there is a class of such examples which fuels the whole thing. That is, gives the how to say cache motivation for the whole thing. But theorists often only have examples that they need to use for refuting conjectures or confirming conjectures. And
yeah, I have to. I understand. Now I must confirm you this is correct. That the examples or the semigroups which are considered came from the point of algebra, which are interesting for algebra, and not from outside from other things. The most of them. Not nevertheless, I have to say there are conferences which are combined this semigroup theory with computer science, and for example in July there's a conference in Portugal which have exactly the subject to find some relationship between computer science and this semigroup theories.
Like automata, such like things.
Yes, exactly. Automata and such one. Yeah. Yes, okay. And but in yes, this is. But I have to say, the motivation for the semigroups that I consider came mainly from the mainstream, which is studied, and I try to solve the open problems in the semigroups which are studied. Not looking for. No, I have to say, I'm not looking for application in computer science or what, but I think I will also go to this conference in July to Portugal. I'm invited there, but I must pay by myself. But the fourth speaker there, and I will go to this conference. Maybe I get more inspiration to found their relationship to for applications for this one.
Some other questions or comments? Okay, for the people in logic, there are a lot of meeting points, for example, unsolvable problems in group theory, in semigroup theory. Also, different speed of the algorithms, there are such things.
Yeah.
So,
well,
if you're interested in the point of logic, there are a lot of things.
Yeah, I'm talking this sort of examples. For instance, finite fields are largely interesting before they are related to communication codes, where you can correct errors. Yeah. Okay. So this kind of industrially originated examples. Yeah. Yeah. One can get rich if one knows such a source. Yeah. For example.
I think the ideas from the semigroup theory comes from the group theory, and we want to find similar things from group theory to that means the most motivations came from group theory to find some things which is similar in the semigroup theory.
And also there is some impact on ring theory because many results from semigroups, they can be transferred immediately to ring theory.
Okay, of course, because you have one part is ring theory. Okay, yes, yeah, of course.
And also concerning computational problems, for example, doing something with Grobner basis, this is working with semigroups.
Yes, of course.
Some other questions or problems? Okay, no, yes, thank the speaker once again. First talk which we plan to have, but it's not true that there are no other talks before. This is 9th of June, where there will be a talk by Vladimir Dotchenko from Strasbourg, and it will be announced in the time. Okay, now you can speak in any languages. You can stop.
Okay, so now the official part is over. May I congratulate Jörg on his promotion.
Thank you very much.
Now, Jörg, I will officially technically transfer the hosting in the Zoom sense to you, because now you are in a sense in a coffee room talking to those listeners who listen to your talk and want to have a chat with you after your talk.
Okay.
Yeah. And we can switch to our native languages, of course.